Okay, I'm having some technical difficulty displaying this. In the meantime, one thing I want to announce is that if you are not registered for the class, how many of you here are not registered for the class? Okay. How many of you are registered but don't have a seat? Okay. I'm sorry, but I have to ask people who are not registered to not be in the room if there are people who are registered but are not able to find a seat. It's not something I'm happy about, but the class is full, there's a long waiting list, and there's not much I can do. Right? So the class has, this lecture room has a capacity of 400, and the class is full. So if you're not registered, you have to watch it on video and wait for some space to open up. Okay? All right, there should be 400 seats in this classroom, so please make sure that you find a seat. Okay. All right, let me see what's going on with, I'm not sure why this is not connecting. Let me give it one more shot at this. Okay. I'm not able to connect this.
You're not able. I'm not sure how to do that. Let's see.
It should be. Oh.
Go to.
Duplicate. Okay. Okay.
Is that doing it? That may not be what you want, though. Oh, there it is.
Okay. All right. Great. Thanks a lot. Yeah. Okay. All right. Let's settle down. Welcome to 374. I'm Chandra Chekuri. I'm a professor in the computer science department and will be the instructor for this course. So we'll go through some basic administrative stuff and then get started with the content proper. So a lot of the information is on the website, which is something that you can easily find. It's a large class, as you know, right? We have a big staff. It's a lot of teaching assistants, a lot of graders, and undergrad course assistants. So check the website. And because the class is so large, we don't want to see too much email directed at individuals, all right? So for most questions, please use Piazza for generic questions, and if you have something that you want to address directly to us, use the private note feature on Piazza so that we can track it, so that we don't forget, and things like, I want a conflict exam, or, something happened, I'm not able to access something, right? But if there's something specific which you don't want to leave on a public place, like some health condition or something that is very private, do send email. Okay. So for basic things, try to not send email to us. Okay. What else? The homework submission will be on GradeScope. I'm not sure if you are all familiar with it. It's a new service that is convenient for grading and submission. You can look up the link on the website. And since GradeScope is not yet what's called FERPA approved and we don't have an official connection to them, if you are not comfortable revealing your information to GradeScope, create an alias and tell us what it is. Okay? There's a link on the course website to tell us how to link your name on Gradescope to your real net ID. Okay? So you don't have to use a real name on Gradescope. Create something that you want and tell us what it is. Right? So that's the way you can set up a link. And we'll use Moodle for quizzes and solutions to homeworks and to give you grades. Gradescope also has grades, but for exam grades and so on. The website has a lot of information. You need to look at the basic features. I'll quickly go over some of the things that we need. The course prerequisites are 173 and 225. And it's not just that I took the course. This is, as many of you know, it's a technically challenging course. It's a fast-paced course. So if you did really poorly in 173 or 225, you should retake it or make sure that you have caught up on the material. Okay, so that's important. There's no textbook. There are a lot of the course is based on many different pieces, so we recommend some books. If you're interested, you can look at them in the library, but we'll provide lecture notes and slides and so on. Okay, but it's always a good thing to read books that are classics and so on. So all of these are very, very important and well-known books. And the more importantly, they have a lot of nice collections of problems, so you can practice on them and not just on homework. Okay, here is a rough grading policy because this is something that all of you care a lot about. So this semester we'll have quizzes for your self-study, but there is no credit for it. It's up to you. And roughly homeworks are at 28%, 2 midterm exams, and the final exam, which is cumulative, and 30%. Okay. Whatever we do, we tweak this, it doesn't really change much, right? So these are just rough numbers. So the midterm dates are already fixed. So put them in your calendar. Don't come to me one day before the midterm and say, oh, I have an interview call scheduled. Okay, that's not a valid excuse. Okay, you need to put this on your schedule and make sure that you don't schedule events around it. Okay, I mean on that day. Okay, we'll have the conflict exam one day after that, and you should have a valid excuse for that. All right. Homeworks, one every week, roughly about 11, including homework 0, which is supposed to be done individually, not in groups. And the rest of the homeworks can be done in groups of up to size 3. You should look at the course policies about collaboration, academic integrity, which is very important. So I won't go through all that, but I expect you to read that on the website. Okay. Homework 0 is on the website. So no extensions for any reason. Okay, if you miss the deadline, that's it. Okay, and it's on Wednesday at 10 a.m. And because it's pretty draconian, we are going to drop basically roughly 3 homeworks. Okay, so the way it's going to work is that you'll have 3 problems in each homework. So it's roughly 33, right? And we'll take the top 24. So you can choose. You may do only 2 on a homework, however you want to do, but that corresponds to 3 full homeworks. So if you use it up early on and you fall sick later on, unless it is some serious illness, we won't excuse it. Okay? So use it wisely. An important aspect is you need to read the instructions on where to submit, how to submit. And it's not complicated. You have to submit PDFs on Gradescope. Okay, it's a very nice interface, and that's also the place where you ask for regrade requests. Okay. So as you know, when you registered, the course has 2 discussion sections per week, one on Monday, one on Friday. So at least at the beginning of the semester, you should go to your assigned discussion section. Maybe, after the course settles down, if you want to change and there's room, you can change the discussion section informally, but don't do that at the beginning of the semester, okay? It's very important, some of you may not find it useful, but many of you will find the discussion sections useful. So I recommend that you go regularly and make use of the time solving problems and talking to the TAs. Okay, advice, long list of advice, right? But the main thing is this is a theoretical course. Okay, it's an important course in our view. It's as you know, algorithms are very, very important in these days. Maybe if you don't really care about the intellectual basis of that, you may even care that you will get a better job if you interview well in good companies, right? At least it's self-interest, right? Yeah. But it's also tough material. It's not just tough because we're trying to make it tough. It is genuinely hard material. So you need to work hard, but you also need to sort of be interested a little bit. It's not a subject that you can easily do if you just want to mechanically do it. Somehow you have to generate that interest. Okay, that's part of the issue. Okay, the one thing I recommend is, which a lot of you, because you're a new generation, right? As I can see, a lot of you have your phones, your laptops, and stuff, right? The course is really about writing with pen and paper, right? It's all about writing, right? Over 70% of the grade is home exams, right? And it is not multiple choice. It's you have to write, okay? And you're graded on that. And a lot of you only write during the exam. Right? But if you do that, then you're trying to do something 3 times during the semester without practicing the rest of the time. So it's very important. This is the advice I give to students who come after they do poorly in an exam. Right? I'm going to do it up front. That learn to write. Okay? Don't type, because that's not how you're being judged in the exams. Right? Maintain a notebook. Right? The temptation for all of you is, oh, there are 3 homework problems, so we have a group of 3. You do 1, I'll do 2, I'll do 3, right? But then on the exams, you don't have your friends, right? And that's most of the grade, all right? So it's important that you maintain your own notebook, you maintain your own way of understanding how to solve problems. We only give 3. Do you know why we only give 3? Because we don't have capacity to grade, not because we think 3 problems are enough, right? It's only because of our limitation to grade. So it's more relevant for you to actually solve your own problems and then discuss with your friends and maintain that connection to your hand. All right? And I won't repeat it because it's very simple. Okay, homework 0 is already on the website. You should take a look, and it's supposed to be done individually, and it's a way to check whether you have the prerequisite material down. Okay. If you have, yeah? It should have 400 seats. That's what I said. There are people who are maybe here but not registered. I'm not sure, because the capacity, official capacity of this room is 397, and they're not 397. They're less than that registered students. Is there a spot that? See, the lectures are taped, so those of you who are not registered have a chance to watch it. Okay, so please, I'm not going to go around verifying registration, but is that all right? I understand it is an important class for many of you. Some of you are graduating, but the academic office is in charge of tracking all this. There's the CS students, WE students. There is no way I can maintain wait lists and make sense of this. Okay, so please contact the academic office and they'll help you. Right? Okay. A lot of you like to watch things on tape. It's up to you, but I recommend coming to lecture. It's obviously, more relevant to me that way, but it's up to you. I think it's more, it's a pain to actually watch videos, for me at least, right? But it's your choice, okay? Okay, that's all about Administrivia, right? You know, I recommend that you actually check Piazza at least once a day for important announcements, corrections to homeworks, you know, things like that. You know, it's your responsibility to check once a day, all right? That's how we will communicate various things. All right, what are the course goals, basically, right? Basically, two important things. First is the design and analysis of algorithms. Okay, what is an algorithm? You know, what is an efficient algorithm? What is the notion of efficiency? And we'll learn some fundamental algorithmic techniques, basically recursion, dynamic programming, divide and conquer, greedy algorithms, graph-based algorithms. Okay. And techniques as well as specific fundamental algorithms that are widely used, which can then be used in various other reductions and so on, right? And then the other part of the course is about theory of computation or computational complexity, is to make sense of what exactly is computation. Is there a formal notion of computation? Right? You know, we use computers. Is this the only way to build a computer? And are there any consequences of defining a formal model? And why are there problems that we would like to solve, but it seems like we don't have an efficient algorithm? Other problems is every problem that we can conceive of computable? And is that a valid question, right? So that's the other part of the course, okay? It kind of goes hand in hand with algorithms, because if you are trying to design an algorithm for a problem and you fail, it may be not because you're not clever enough. It may be that there is no algorithm, okay? So to be able to argue that, you need to be able to understand what is actually a computer, right? How can we mathematically argue about what a computer is, right? So that's really the two high-level parts of the course. And the course is not structured in the way I said, but it's structured into three parts, right? The first part of the course, till midterm 1, will deal with what's called a language theoretic view of computation, and in particular, we'll discuss very simple computers called finite state automata, and we'll introduce some multiple ways of looking at this very simple class of languages, which finite automata accept, and they're called regular languages. And then because the course is compressed, we'll talk very briefly one lecture on context-free languages and grammars, and then we'll also introduce the formal model of computing called Turing machines, which many of you heard of Turing, if not for anything else, because of the recent movies, I guess, and he's a very famous man. The second part of the course, or the second third of the next third will be on algorithms, right? You know, algorithm design, and the last part will come back to computational complexity and show why certain class of problems are intractable. There are classes of problems which we don't have any algorithms for, and then there are classes of problems where we don't have any efficient algorithms. How do you reason about that? And then we'll talk about two types of intractability. Undecidability is a notion that there are problems for which there are no algorithms. And NP completeness is a notion that there are no efficient algorithms known under a particular possible conjecture. Okay? So how do we prove that some problems are hard? So that's the last part. Okay? And in anything, you know, in the long run or in the short run, right? You know, the big thing we want you to get out of this course is how to think systematically about algorithms, right? The notion that you should think about solving problems in an algorithmic way. How do you think about it? If not, you know, most of you probably will not end up designing algorithms, new algorithms for your living, but you will use algorithms all the time. If you do any kind of computer science, or even if you're not doing computer science, if you do any kind of work with data these days, you have to think about efficiency, right? You have to think about, you know, how to model things, right? And even if you want to just model and use off-the-shelf algorithms, if you have an awareness of what is possible, it will affect the way you look at things. Okay, right? That's the main thing we want you to take away from this course. Okay, And you know, historical motivation for computing informed the development of the models of computing. You know, I think the two big things, you know, people have always wanted to do calculations, right? They wanted to add numbers fast. They wanted to do many calculations fast, and that was one historical motivation for people to think about computing. But another important historical motivation came from mathematics. The notion from Hilbert at the beginning of the 20th century is, can mathematics be completely automated? Okay, so that was an important motivation for computing. And this led to the notion of what is really a computing, right? And there is so what we'll do in this class is discuss the mathematical model of computation versus the computing devices, which are actually what we use, right? Which are the physical devices that realize this mathematical model, right? So we'll be mainly focusing on the models and not obviously on the devices, because that's not the content of this course. And I just want, this is just some high level comment that, you know, so the notion of, you know, what is a computer is not decided, right? In the sense that, you know, we accept Turing machine as a model of computing, but that's not a mathematical theorem. That is the model of computing, right? That's just a hypothesis. And people also, you know, we also have to pay attention also to things about building things. In particular, for example, you know, we're not going to discuss it, but, you know, some of you may be interested in quantum computation, right? And so what is quantum computation? Well, does it do anything to our model of computation? Can they do things that we're not able to do today? And the motivation for thinking about quantum computation came from physics, right? And so physics inspires models of computation, and also physics helps us build computers, right? But you know, we will stay at a slightly higher level, right? We are not going to really discuss the building of these things. And if you're interested, you should follow up on later courses. Okay. Okay, and before I get into some nitty-gritty, let me tell you why this the subject is not as simple as it sounds, right? By giving two simple, one on algorithms and one on undecidability, right? So let's take addition, right? We all know how to do addition, right? Okay, at least, you know, this is what I teach my 8-year-old, right? How to do addition. Okay. So let's think about it as an algorithmic problem. Well, you know, when we think of addition, we think of small numbers. But if you want to think about computation, you should think of big numbers, right? You know, if you have only, like, you know, 5-digit numbers, there is nothing interesting going on, right? So as an algorithmic problem, how should we think about addition? I have one n-digit number and another n-digit number, and I want to add them, right? Okay. Okay. How many steps do we need to add to n-digit numbers? Now, what is a step, right? That's now automatically, right? Okay, so that's where, you know, you have to think about, okay, what is an elementary step we can do, any kid can do, right? Is they can add 2 digits, right? That's the first thing we learn, right? Okay, so one elementary step is just, let's say, you know, adding 2 digits. How long does it take to add 2 n-digit numbers as a function of n, right? Well, you know, that shouldn't be so hard, right? How long does it take? If I give you 2 n-digit numbers and I want to add them, and my primitive operation is to add 2 single digits, how long does it take? Roughly n time, right? Yeah? Okay, not hard, right? Okay, all right. Okay, this is, addition is easy, right? Okay? Okay, now let's do something a bit more interesting, right? Well, okay, why is addition, why is it done, right? In some sense, n is a time to just even read the numbers, no? So it is just, you can't do better than n, right? Because you just have to read the input, right? Look at the numbers, taking that itself, scanning the numbers itself takes n time. Okay, what about multiplication? That's a bit more interesting, no? It's not so simple, it seems, or unless, you know, How do we learn multiplication? Right? This is how at least we teach our kids, and this is how we do it, right? If you have to do a multiplication by hand, this is how will we do it, right? We do it the grade school way, right? You take one digit, multiply the number, right? How long does that take? If you have I'm trying to multiply two n-digit numbers, right? One digit and multiplying the n-digit number takes n time roughly, right? Yeah? Okay. And then I stack them up, right? And then add them up, right? So how long do you think it will take as a function of n? Yeah? Yeah, roughly n square, no? Why does it take n square? Yeah, we can do it in n square time, right? Why? Because we have n now. How many numbers do we generate in this step? We have n-digit numbers, right? And then we have to add them up, no? Right? So it takes n square time, right? Okay. So is that the fastest way to multiply two numbers? Okay. If I come to you and say, okay, what is the best algorithm to multiply two n-digit numbers, right? So we know an n square solution, and I take n to be very big, say, billion, right? I don't know why you would want to do that, but say, we have that, right? As a fundamental problem, you say, how should I multiply two? I ask you to write code, and for some reason, I want to multiply billion-digit numbers, right? Okay. Billion is not so big, but it's pretty big, right? N square is slow, right? In some sense, billion square is going to be slow, right? So we would like to speed it up, right? If we can. But more importantly, it's not just the fact that, it's useful or something. It seems like, multiplication is so simple, right? We do it all the time since we are kids, and this is how we learn it, right? It seems like it's almost axiomatically, what else would you do, right? It seems like, what are you talking about? There's no other algorithm. This is the way I learned it, right? But it turns out that you can do it much faster, okay? How fast? Okay. This is what we know, okay? You can do it roughly in n log n time, okay? All right? And it is not at all obvious. Okay? It's not at all obvious, okay, how to do it in n log n time, right? We're not going to be able to cover this topic in this class because it is not obvious. Okay? You take 473, I covered it a little bit on 473. It's not that it is super complicated, but it is not obvious. Okay? The point I want to make only is that even multiplication, which we learn in grade school, when you think about it algorithmically, is not obvious. What's the fastest algorithm to do it? Okay? And it requires, some understanding of non-trivial mathematics to come up with that algorithm. And we still don't completely understand how fast really the fastest algorithm for multiplication. All right? So that's one point I want to make, that even obvious things, seemingly obvious things are not so obvious. Okay? And so that's why computation and algorithms are tricky. You can never tell so easily what is the right answer. So here is another problem. Okay, it's called post correspondence problem, right? And it's very simple. So what is it? I give you tiles like that, right? So each tile has one string on the top and one string on the bottom. Okay, that's the input. Okay. So you want to know whether you can take those tiles and stack them next to each other, like we shown in the bottom picture, right? So that the string on the top and the string on the bottom are the same. Make sense? Yeah. So is it in this case the string on the top and bottom are the same, right? Okay. So what is the problem? The problem is I give you tiles like that, and you have to check whether this is possible or not. Like in this case, the answer is yes, right? And it's easy to create tiles where it's not possible, right? Why? Because I put a tile on top which is A and bottom is B, right? Or the alphabet also need not be the same, right? It's easy to create tiles where the answer is trivially no, right? But in this case, the answer is yes, right? So this is the algorithmic problem. Okay? So if I give it to you when you're in your freshman or when you took your first programming class, or even after 225, you may try to actually create some code for this, right? So I'll come up with a heuristic and try to solve this, right? Okay. The thing is, there is no algorithm for this problem. Okay. Does it make sense? What does it mean? There is no algorithm for this problem. Right? When I say there is no algorithm for this problem, I'm claiming that on our current computers, there is no, I can prove formally that there is no algorithm which will always correctly give the right answer. Okay? It doesn't matter how long it takes. Okay? It's not the question of running time. It's not exponential or whatever. There is no algorithm, and we can prove it. Okay? It's not obvious, no? It looks like a simple problem, right? It's just a string matching problem, right? The fact that means that whatever code you write is going to fail on some input. Either it will go into infinite loop or it will give the wrong answer. Okay? It's not that it's inefficient, right? So we can prove that. Okay? Okay? And that should surprise you, right? Because it seems like a very simple problem that our computer should be able to solve. But we can prove that this very simple looking problem doesn't have any algorithm on our current computers. How can we prove that? Well, that requires us to understand what a formal model of computation is and the Turing machine model and stuff. And here is another problem, right? Which, we wish we have in our programming courses, right? The simple debugging problem, right? I have a C program I'm trying to check, I'm going to submit to in 125 or something, and it says, I'm not sure, whether it'll work or halt or properly, right? So it's a very simple and very important problem, right? We would like to solve this, right? Forget about our own selfish interests. If you think about software engineering, wouldn't they like to solve this problem? I mean, they would want to solve this problem, right? Yeah. It turns out that this is not solvable, right? Even simpler problem, I give you a program and say, will it print hello world? No, these are not solvable problems. What does that mean? That there is no algorithm which will always correctly give the right answer for this problem. Okay? And that's I mean, this is maybe more believable because you say, oh, that's a very difficult problem because it looks difficult, right? Oh, I mean, we're talking about reasoning about all programs, right? Maybe my program is very complicated and how will I know whether it will correctly do what it's supposed to do? So this seems on the face of it a more difficult problem, right? While the previous problem looks like a puzzle, right? This looks like a puzzle, right? Which is approachable because, what about it? Just dominoes and tiles, while the debugging problem, at least on the face of it, looks hard, right? So the point is that one can show that if you can solve this problem, you can solve the debugging problem. That's how we show that this cannot be solved. Okay, all right. So that's the important, another important aspect of algorithms and computer science is this notion of reduction, that things that don't look similar are actually equivalent, right? On the face of it, you can't tell that this problem and the debugging problem are somehow connected or even related to each other in any formal way. But you can show that this is a hard problem because you cannot, if you can solve this, you can solve the debugging problem. Okay? So that is the very important aspect in algorithms of the notion of reduction, that you transform a problem that you want to solve into another problem that is either solved already or we know is already that we'll use two ways to use reductions. In one way is that we'll take a problem that we want to solve and say, look, I can transform this into a problem like a graph problem that I know already how to solve. Right? That's good because then you don't have to reinvent the wheel. Right? You're using existing knowledge to solve new problems, which is what we want to do because there are so many gazillions of algorithmic problems. You don't want to create a new algorithm each time. Right? But we'll also use it to show that, look, this is hard because if you can solve this, you can solve the halting problem, which is easy to show is hard. Okay? So we'll use reductions in both ways, and it's a very important way to think about algorithms. Okay, so so the reason why I put these two simple problems is that simple-looking problems is that the notion of algorithms, even though it's simple and we start with very basic things, it's not obvious how to design algorithms. And that's why we learn the skills. You need to learn a variety of skills to help you figure out what's doable and what is not doable. All right? So, all right. So that is philosophy, right? And from philosophy down to very basic things. All right? So, any questions before I switch into nitty-gritty? Okay. Yeah? All right? Okay. So, now we're going to switch into something very, very basic about strings and languages. It will be just a lot of definitions, a lot of simple looking stuff, but it's important for you to make sure that you properly understand this stuff, because you will be working with this all semester. Okay. All right. So let's start with the notion of strings. Okay, we all know what strings are informally, right? So what is an alphabet? An alphabet is a finite set of symbols. Okay. What is a symbol? That's just that's an axiom, right? A symbol is just an atomic thing, right? Okay. So for example, 0, 1 is an alphabet, right? It's important. It's finite. And A, B, C, D, the letters of English is another alphabet. But I intentionally put that, look at that move forward and move back, right? That's an alphabet too, right? Because we think of that symbol, move forward, as a symbol, not as a string itself, okay? It's just some atomic object, right? So what is a string? A string is a finite sequence of letters from the alphabet, okay? Very easy to understand. The length of the string is easy to understand. It's how many characters are there, because it's finite, it's well defined. Epsilon is the empty string. Okay, very important. Epsilon is the empty string and its length is 0. Okay, and then we'll use this notion of exponentiation, that sigma to the n is the set of all strings of length exactly n. And sigma star is the set of all strings. Okay, we'll formally define that. Okay. Now, so it's very easy to understand the definition of a string, because we kind of see it, right? We see it, whatever that means, right? But seeing is not the same as formally having a definition, because when you actually want to prove something, you need to have a formal definition of what a string is, right? So we define strings inductively, right? We start with saying the epsilon is a string of length 0, and then we say that, a string is either epsilon or it is ax, right? Where a is a letter from the alphabet and x is already a string, right? So we build up strings inductively of increasing length, right? So why is this important? Because when you want to use induction to prove something, you need to have a formal definition of what a string is. Okay, so this is a formal definition of a string. Okay, convention. Again, we are here at meta level. We'll use A, B, C, the initial part of the English letters, to look at the alphabet, and we'll use strings W, X, Y, Z. It's just a convention, and we'll use A, B, C, the capital letters, to denote sets of strings. Okay. Okay. Just to make sure that we understand epsilon, right? Even though it's okay, people get very confused, and it's very important to make sure you one of the skills, again, pen and paper. When you write programs, right, the compiler is very harsh on you, right? If you write nonsense, it will kick you out, right? Unfortunately, in mathematics, the graders, the instructors, we can't be so harsh, right? But we want to be harsh in this class with your notation, because if you don't write properly or don't understand the concept properly, the differentiating a set from an element of a set and things like that, you're not doing proper type checking. Okay, we cannot. I mean, we should be like a compiler, right? Unfortunately, we are human beings, right? So we can't. But we will be tough, at least in the beginning, so that you get good habits. It's not because we want to be tough. Just like the compiler is trying to make you write better code, we want you to reason well. Right? So be careful about mathematical notation, just as you would with programs, right? Okay, epsilon is a string. It's not a set, but the set containing epsilon is a set, right? The epsilon is an element there. Okay, empty set has no strings, and that's a set containing an empty set, right? So that's a one element set. Okay, so you have to be careful about these kinds of things. Concatenation of strings. You know, if you know what a concatenation is, you know, if I take two strings x and y, and xy is a concatenation of x with y, which is a unique string obtained by putting y at the end of x. But formally we'll define it as follows: xy is y if x is epsilon, right? And xy is a wy if x is aw, right? Here, why is it important? Because see, we are here using the formal definition of a string itself to define concatenation, right? What is a string? It's either epsilon or aw, where a is an alphabet, a letter of the alphabet, and w is a string, right? So we are using that here to define concatenation formally. Okay, okay. And you know, we normally write xy as a concatenation, but sometimes we'll write x dot y to indicate that it's actually an operation on two strings, right? It's to be formal, it's an operation on two strings giving rise to another string. And it's easy to prove using the definition that concatenation is associative. uv concatenated with w is the same as u concatenated with vw, right? Okay, and but it's not commutative, right? uv is not the same as vu, right? Okay, and for any string u, epsilon u is the same as u epsilon is u. Okay, substrings and prefixes and suffixes. What is the prefix of a string? It's the first part of the string, right? Suffix is the last part of the string, right? A substring is something which can be in the middle, right? Formally, v is a substring of w if w can be written as xvy for some strings x and y. Okay. All right, and if x is epsilon, then v is a prefix. If y is epsilon, v is a suffix. Okay, then you know we define exponentiation of strings inductively, right? What is w to the n? W concatenated n times, right? Right? Yeah. Okay. All right. So blah to the 4, right? Blah 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 blah. Okay. Okay. Sigma star in languages, okay, given sigma, the alphabet, sigma to the n is a set of all strings of length n. Again, we can define it inductively as sigma to the n is epsilon, is a set containing epsilon if n equal to 0, and sigma to the n is, I didn't do this, okay, let me do this, okay. Okay, we define concatenation of strings, right, x and y. We understand concatenation of strings. What is the concatenation of two sets of strings? Now, A is a set of strings and B is a set of strings. Okay, so we define the concatenation of sets of strings as take every string in A, every string in B, concatenate them, you get a new thing and put it in the set. Okay, it's a new set. Okay, so AB is xy where x belongs to A and y belongs to B. Right, for every pair of x and y where x is in A and y is in B, we concatenate them, put them in the set. Okay, all right. Okay, so that's the set concatenation, and you can see an example there, right? And once you have set concatenation, we can define sigma to the n formally as sigma to the n is simply epsilon if n equal to 0, the set containing epsilon, and otherwise it is a concatenation of sigma. Now sigma is being overloaded here as a set of strings, okay, with sigma to the n minus 1. Okay. And sigma star is a very important definition. You may think it's trivial, but what is sigma star? It is a set of all strings, okay? And you have to be a little careful. It's a set of all finite length strings. Okay? Formally, it is a union over all n greater than or equal to 0 sigma to the n. Okay? So there are no infinite length strings in sigma star. Okay? And infinity will play an important role here, and we'll discuss some subtleties there, right? What is sigma plus? It is all the set of all strings of length at least 1 in sigma star. Okay, so we remove epsilon basically. Okay, we don't want epsilon. Okay, all right. Now, what is a language? A language is simply a subset of strings. A language is simply a subset of strings. Otherwise, mathematically, L is simply a subset of sigma star. Okay? All right. Okay, now all that seems like, come on, it's so simple, trivial, right? Let's do some exercise. Okay? Okay, sigma is 0, 1. What is sigma to the 0? Yeah? Just a set containing the empty string, right? Yeah? But where did we get that from? Why is that correct? This is from the definition, right? Yeah? You didn't make it up. This is a definition. How many elements are there in sigma cube? Sorry? 6, 8, 10. What is sigma cube? What is your understanding of sigma cube? Sorry? No, I know. I'm not asking. What does the sigma cube mean? All strings of length? Exactly 3, right? Okay? Yeah? So, and there are 2, the size of the alphabet is, so this is basically this, right? Okay? This is 8 here, okay? How many elements are there in sigma to the n? Yeah? Okay. Yeah? What is the length of the longest string in sigma star? Should be sigma star. Quick question. Yeah? Yes? I can't hear you. There is no longest string, right? Why? I mean, what is the largest number in the integers? There is no largest number, right? Because the integers keep on going, right? Okay? There is no longest string in sigma star. Does sigma star have strings of infinite length? Oh, okay, that's very important. Okay, if there is a string u of length 2 and v of length 3, then what is the length of the concatenation? 5, 6, 5, okay. Let u be an arbitrary string in sigma star. What is epsilon u? What is u epsilon? Okay. Is uv equal to vu for every uv belongs to sigma star? Okay, no. Okay. What about the next one? Yes, right, because it is associative. Okay. All right. Just to all right. Here is an important concept which we'll very much need. We have done this in 173, but it's important, right? So we'll be dealing with infinite sets, right? Because otherwise, finite things are not very interesting when you talk of computation, right? We'll see why. But there are different types of infinite sets, right? So we have to be a little careful. So how do we compare two infinite sets, right? Are they the same size, right? It's a very fundamental question that came up in foundations of mathematics, right? It's like they say, okay, integers are infinite, right? And real numbers are also infinite. And so people wondered, is real numbers bigger than integers? How do you figure that out, right? So a more simpler question is, what about the set of even numbers, right? Are the set of even numbers bigger than the set of integers, or are they smaller? Right? It's a little tricky question, right? Because the set of even numbers is a subset of the set of integers, right? Even integers. But but it's also an infinite set, right? How do we compare two infinite sets, right? How do we count, right? We can't count, right? So how do we say that this set is bigger than that set? And it is important because we will see it comes up, right? You know, it's not something we are doing for the fun of it, right? And so this is a very important question in mathematics. And then Cantor came along and he said, okay, you know, let's define two infinite sets to be the same size if there is a bijection between them. What does I mean bijection? That is a one-to-one mapping between them, right? So we can point this way, right? Okay, and so then we say, okay, let's define a set to be countably infinite if there's a bijection with the integers, because integers we can't think of as basic objects, right? And that we count using integers. So we'll call an infinite set countably infinite if there's a bijection with the integers, right? So that's the definition of countably infinite. And one other way of thinking about it is, when is a set countably infinite, right? It means that there's a bijection with the integers. That means that we can look at the elements and order them in some way. This is the first element, this is the second element, this is the third element, this is the fourth element. And we look at the ordering, and every element should come in the ordering somehow, somewhere. Right? That's another way of thinking about a bijection with the integers, especially, right? So, are the set of even integers countably infinite? Why is that? You can write down, right? 2, 4, 6, 8, and that's you can see that every even integer will come there, right? Somewhere. Okay. So what about? So my claim is that if you fix the alphabet to be finite, then the set of all finite length strings, set of all strings is basically also countably infinite. Okay. Have you seen this before? Okay, it's not hard, but we'll do it. We'll see. This is the proof, right? The proof is, take 0, 1 for simplicity, right? One way of seeing it is, okay, every string can be mapped to a number, right? That's the easy way of seeing it, but let's see it a little bit more slowly, right? This is because this is useful for us. So I want to claim that the set of all strings, finite length strings, right, is countably infinite. That means I can order them, yeah? No, I will come to that. I'm not there yet. Okay. Okay. So this is the same as saying that all even integers is countable, right? So what should I do to prove to you that it is countable? I need to tell you how to order the strings in such a way that every string will be there in that ordering somewhere, right? Okay. So here is how I'm going to order, right? Take 0, 1 to the alphabet. It's the same for every other alphabet, finite alphabet. You simply order them first, the strings, by the increasing length. Okay, what is the length 0 string? Epsilon, right? So that comes first. Then what are all length 1 strings? 0 and 1, right? Okay. Now, how should we order 0 and 1? Okay. Okay. Here we have to think a little bit. Let's put 0. First, we'll order the alphabet somehow. Okay. Let's assume that alphabet is ordered such that 0 comes before 1. Okay. Then we'll put 0 before 1 because they have the same length, but 0 is before 1 in the alphabetical order, right? Okay. Now let's look at all strings of length 2. How many of them are there? 4 of them, right? 0, 0, 0, 1, right? 1, 0, 1, 1. We'll put them in that order, and this is called the dictionary ordering, right? If you have 2 strings of the same length, order them according to the dictionary ordering. What is the dictionary ordering? We all get used to dictionary ordering, right? What is the dictionary ordering? If you have 2 strings of the same length, A comes before B, B comes before C, right? That's how we order, right? Because we are using the ordering on the alphabet to create an ordering on strings now of the same length, right? So now we do strings of length 2, and then we go to strings of length 3, and so on, right? Now this is an ordering of the strings, and it's easy to see that every string will come in this ordering, right? If there's a string of length n, when will it come in the ordering? What is an upper bound and when it will come in the ordering? Right? Every string has some finite length, right? Say its length is n, then the only strings which are coming before it are how many are them, right? 0 plus 1 plus up to 2 to the n minus 1 plus maybe 2 to the n, it comes last in that length. But definitely every string will come in this ordering, right? Okay, so this is a proof that for any, of course, if the alphabet is not size 2 but of size 10, it doesn't change much, right? The number of strings of length n is 10 to the n if the size of the alphabet is 10, right? Okay, for every fan. Does it make sense? That is right. Okay, so it's called countably infinite. Okay. Now what about this? This is an exercise for you, right? Now I'm interested in pairs of strings. Okay, to make you think about 173, in 173 you probably proved that the set of rationals is countably infinite. What is the set of, what are rational numbers? A by B, right? Instead of thinking of A by B, you can think of it as A comma B, right? Okay. So instead of thinking of integers and even integers, if I told you that, I'm interested in tuples of numbers, A comma B, right? Why is that countably infinite? So my numbers are 1, 2, 2, 3, and so on, right? Can you use the same trick to argue that the set of rationals is, forget about this, set of rationals is countably infinite? How should I order tuples? I mean, you've seen this in 173, so it's not completely new, but I'm just recalling. Yeah? Sorry? No, that's a proof to show that the power set of the natural numbers is not, I mean, maybe I'm misunderstanding the word diagonalization, but diagonalization is a proof technique to prove that the power set of the natural numbers is not enumerable, right? But I'm not asking that. I'm asking you to prove that the set of numbers, natural numbers times natural numbers, is countably infinite. Okay? Or rationals are countably infinite, right? Yeah? I mean, I'm looking at this, right? I mean, I'm going to look at only positive ones. We can do the negative ones easily. Okay. Sorry? Yeah, I'm asking you to prove why rationals are countably infinite. Yeah, one. Yeah, that's right. So what we're going to do is that we're going to order them by sum of A plus B. Okay, 0, 0 comes first. So we'll order them by, look at all A, B. Look at these are all positive, right? So order the numbers by sum of A plus B, just like we did with the length here. So what is the sum of A plus B equal to 0? How many numbers are there? Just 0, 0, right? Okay, that comes first. Then what are all now tuples, pairs which have sum equal to 1? 0, 1, 1, 0, right? And then 2. So you have more numbers, but 3 and so on. That's it, right? So again, it's the same idea. You order the numbers by sum of A plus B, okay? And every tuple will come, right? Yeah? Okay? So now, what I want you to do later on, not now, is to use the same idea, combine these two ideas to show that even tuples of strings are also what? Countably infinite. Can you do that at home? Yeah? I think so. Or you should. Okay, that's an exercise. And not just tuples, you can also do it with 3. Tuples of length 3. Okay, same idea, right? If I gave you n times n times n, that is also countably infinite. Okay, n times n up to 4. Any finite tuples are all countably infinite. Okay, same idea. Okay, you should figure this out. Okay, okay, yeah. Yes, exactly. Yeah, that's right. Okay, yeah. So you can find bijections in any way, but that's the simplest way. Okay, all right. Okay, now I'm going to. Oh, it's all at 12. I'm going to do induction. Okay, you'll say, oh, didn't we learn it as babies? I mean, why is it doing induction again, right? But this course is all about proving things by induction, and okay. And many of you learn bad habits about induction, which we hope to fix in this class, right? So I'm going to do something so simple, but it's important to understand the concept, right? So the first part of the course, especially, there's so much induction that let's go over it slowly, okay? Everybody knows what the reverse of a string is, right? If you say, yes, sure, right? But how do we define it formally, right? Because induction follows formal definitions which are themselves inductive, right? So it's important. So what is the reverse of a string? How do we define it formally? We define it as follows. The reverse of a string is epsilon if the string is epsilon, okay? And remember, the string is either epsilon or a times w, right? That's the inductive definition of a string, right? So how do we define if the reverse of a string which is written as w is ax, then we define it as x reverse concatenated with a, yeah? Okay, easy to understand the definition of reverse, yeah? Okay, now I want you to prove this, this theorem, or a simple theorem. For any two strings uv, the uv reverse is v reverse u reverse. Is it obvious? I mean, you can see it, right? You know, if you play with things, yeah, oh, sure, yeah, right? But I don't want you to see it, I want you to prove it, right? Okay? There's a difference between seeing and proving. Why? Because seeing can be dangerous, right? Well, proving is less dangerous. It's not always, you know, we can obviously create wrong proofs, right? Right? Okay, more than that, it is to get skills at proving, right? Simple things like that, like this, we need to. Okay, how do you prove it? How do you prove, right? Yeah. By induction. Why is it by induction? Because there is no other notion of, we define the thing inductively, so there is no choice for us, right, more or less, right? Unless it's so simple that you can prove it otherwise. Okay, so we'll do it by induction, right? You know, and why, what do you know, when we see, you know, so induction, you know, just briefly, is to prove statements of the form for all n greater than or equal to 0, some property P, some statement P of n is true, right? Induction is used to prove for all kind of statements, okay? So, I mean, the simplest example we all start with in I don't know when, but we start with this simple formula, right? And say we learn how to prove this by induction. But then, you know, it's a kind of a bad example to start with, right? Because it does it makes it look too easy. But anyway, the template is you prove base case, and then you prove the induction step. You prove the case in this case P of 0 by some way, right? Maybe that will involve a complicated proof itself, right? That's a separate part of the proof. And then how do you prove something by induction? You here is how you prove it. Let n greater than 0 be an arbitrary integer. It's very important that it's an arbitrary integer, right? And then assuming that pk holds for 0 less than k less than n, 0 less than or equal to k less than n, prove that pn holds. This is your job, right? This is part of the proof, right? Is here n is arbitrary, and this is what's called, this is called strong induction. We'll only use strong induction in this class. If you use weak induction, you know, you'll see in the class website you'll get a 0, okay? And there are good reasons for that. Okay, now the problem is, when you learn induction like this, most of the things you want to prove don't look like this. Okay, nobody is going to tell you this. See, right, what do we want to prove? We want to prove this, right? It looks like this. That doesn't look like what the template says, right? That's where, you know, we have to be a little bit more careful. And you'll see things like proof by induction on what, right? You'll see proof by induction on length of u, on length of v, on length of u plus v. What does it mean, right? So I know that many of you are confused by that, and so I want to go slow. So here is what when people say, when they say proof by length of u, what are they really saying, right? They're saying the following. If you want to prove by induction on length of u, it's really what you're proving is this. Okay, what is this? You're changing what you want to prove into the template. What is the template? For all n greater than or equal to 0, P of n. Okay, what is P of n? Okay, here is P of n, right? If you want to say proof by induction on the length of u, you're proving the following. For every n greater than or equal to 0, for any string u of length n, in parenthesis, for all strings v of sigma star, uv reverse is equal to v reverse u reverse. Okay, I want you to understand that this is what you are proving if you are saying proof by induction on the length of u. Okay, you are translating your original problem statement into something which looks like this. Okay, and one observation is that this itself is a what? Universally quantified statement, right? There is a for all in that. Okay, all right, and outside is for all n greater than equal to, so you're doing induction on length of u, and u is arbitrary string of length of size of length n. Okay, so there are several for all quantifications going on. Okay, now that we have translated that into the thing, let's try to prove it. What is the base case? Okay, what is the base case? The base case is that you should prove this statement for what? All strings of length 0, because there is a for all there. Okay, so how many strings of length 0 are there? Only one, right? But if there are more than one, we have to prove it for each of those cases. Okay, because that's the base case, right? The base case of p of 0. Okay, that's easy, no? Why is it easy? Okay, let's prove it. Okay, so u is epsilon, but remember the inside statement has no, v can be arbitrary, right? Because it's also a for all statement. So you should not assume anything about v if you're going to prove that, right? So I'm not making any assumptions on v. V is just an arbitrary string. So u is epsilon though, because there's only one string of length 0 and u. So uv to the reverse is epsilon v reverse, right? But epsilon v is v, so it's v reverse, right? But v reverse is same as v reverse epsilon, because that's true, right? And then epsilon reverse is epsilon from our definition, and that is the same as u reverse because u is epsilon. Okay, this is easy, right? Okay. Now let's go to the induction. Okay, one important point I want to make is that we didn't make any assumption about v. That's why it holds for all v, right? V was completely arbitrary, all right? It's important. Okay, now let's do it for the inductive step. Let u be an arbitrary string of length n greater than 0. Okay. Assume inductive hypothesis holds for all strings w of length less than n. Since u is of length n greater than 0, right? Remember, we need to prove it for n greater than 0. We can write u as ay, right? Because that's a definition of a string, right? Either it's epsilon or it is a times y for some string y of length less than, right? Okay, and a is something. Then let's do this, right? Okay, what should we do? We write u as ayv reverse, which is ayv reverse, right? Okay, and then can we now use something? What did I use here? I use associativity, right? Okay. Now what I can apply induction? Why? Because a is of length 1 less than the length of u, right? Okay. So I can use induction hypothesis, right? Remember, the statement holds for all strings v, right? Now yv has become v, right? That's important. It's there in the inductive hypothesis, right? Because it holds, that was right. So I can write this as what? Right? By applying induction here, right? Inductive hypothesis. And now what can we do? I can apply induction again, right? To what? Y is of length strictly less than that of u, right? So I can write this again by applying induction, v to the r, y to the r, a to the r, right? Okay, all right, and then what? Now again I can apply induction, right? Oh, okay. What happened here? Okay. Where am I? Okay. I can again apply induction to this string and write this as ay to the r, because a and y are less than thing, and then this is v r u to the r. Okay. right? Simple enough, right? Okay. But what I want you to understand is that it's not hard, but what is important is that you have to translate this into this, right? Okay. And that is very important, otherwise you will not understand what is going on. Okay, then you say, why not apply induction on V? What does applying induction on V mean? So that means I am applying induction on the second part of the input, right? Okay. Okay. What does that do? Okay. So if you do that, then you have to write down for yourself till you get better at it, right? The induction hypothesis is now changing because we are doing it on induction. It says for all n greater than or equal to 0, for any string v of length n, and then in parentheses, for all strings u belong to sigma star, u v r reverse is v reverse u reverse. Okay, does it make sense? When you say that we are going to do induction on length of v, this part changed, right? Okay. Now if you try to prove this by the same proof, you will fail. Okay. Why will you fail? Well, okay, we don't know whether we will fail. Okay, that's the point. When you try proofs by induction, you have to go through the motions formally till you realize that something doesn't work. Okay, so shall we figure that out? Let's see why it fails. Okay, base case works. I'm not going to do the base case. It's simple enough. It will work. But then let's see what happens when you try to prove induction, right? Okay, let V be an arbitrary string of length n greater than 0. Assume inductive hypothesis holds for all strings w of length less than n, right? Since v equal to length of v is n, which is strictly bigger than 0, v can be written as ay, right? For some string y with length less than n, and a is some letter in the alphabet. So then let's try the same thing. uv to the r is u. Now what should we do with v? V will write as ay, right? Okay, so you write ay, and then you say, okay, what are we going to do? We're going to take a to a u, and so by associativity you say u a y r. Now we can apply induction, right? Why? Because the length of y is strictly less than the length of v, right? Okay, and then this becomes y reverse u a reverse. Now what can we do? Can we apply induction? Why not? Yeah? No, we are doing induction on the length of v. Remember, you would like to, you would say, I want to convert this into a reverse u reverse because the length of a is less than, that's only one length, right? Is less than the length of v. Okay? If I write this, what's the wrong, suppose I say yr a reverse u reverse by induction. Why is that wrong? If I do this, I'll be done, okay? Why is that wrong? No, there is a subtle point here. Why can I not apply inductive hypothesis here? Sorry? No, it's not the order. The thing is, how can you guarantee that the length of A is strictly less than the length of V? What if n equal to 1? If n equal to 1, we cannot say that the length of A is 1 is less than the length of V and apply induction. Okay? Small point, but it's very important. Does it make sense or no? So I'm trying to apply induction on length of the second argument, right? So when can I do it? Well, if the length of this string is less than the length of my original V, right? But if n equal to 1, it is not true, right? If n equal to 1, y is epsilon, and we cannot apply this, okay? Okay, so you're stuck, this proof doesn't go through, okay? So what do you need to do? You say, okay, I need to apply induction on, I need increase my base case. I have to prove the base case for n equal to 0 and n equal to 1. If you do that, then the proof will go through. But then you say, how do I prove that the base case of n equal to 1? And you realize the base case of n equal to 1 is actually not so easy. Which means that you should go back to induction on length of u. Okay, but you don't know that a priori. All I'm trying to do is that you don't know that a priori. The second thing is that you can do induction on the length of u plus v also. That also works. Okay, but you can do that in the lab. All right. Yeah, give me 1 second.